Welcome to another Explainer. Today, we are jumping right into a truly groundbreaking study, one that beautifully mashes up artificial intelligence and biology to take on the global climate crisis. We're looking at some fascinating research that proposes a totally innovative way to generate clean, sustainable energy and high-performance materials from, well, something you'd probably never expect.
To really get why this matters, we have to look at the massive global stakes. The world is on this desperate hunt for affordable, clean energy. And this research, it directly answers that call. It aligns perfectly with the UN's Sustainable Development Goals and ambitious national targets like Saudi Arabia's Vision 2030. We are talking about reducing carbon emissions by 278 million tons annually by 2030. 278 million tons? The whole idea here is to build a circular carbon economy, basically a system where absolutely nothing is wasted and everything gets repurposed.
Here's our roadmap for today. First, we'll look at the green energy mission, followed by the magic of Chitosan. Then we'll examine the pyrolysis puzzle, how they brought AI to the rescue, and finally, what this all means for a sustainable future. Okay, let's dive into this.
Section 1. The Green Energy Mission. Building a Circular Carbon Economy. So our modern world has this massive reliance on fossil fuels, right? And breaking that habit is incredibly tough. We urgently need a way to transform biological waste into high-performance biofuels and biocomposites. That's literally the ultimate goal of this research. But it begs the question, where exactly do we find a renewable, abundant source of biowaste that can pull this off? Well, it turns out, the secret to a greener planet might actually be hiding right in the ocean.
Section 2. The magic of Chitosan, the ocean's hidden polymer.
And that brings us to the specific organic material the scientists in this study are trying to utilize. Meet chitin. Scientifically speaking, it's a cationic linear polysaccharide derived from crustacean shells, so think crabs, shrimp, lobsters. It's actually the second most abundant natural biopolymer on Earth, right behind cellulose. But it isn't just abundant. Its highly polar and somewhat unstable chemical structure makes it absolutely perfect for trapping carbon and soaking up heavy metals if it's processed correctly.
Now, what's really interesting about this slide is the elemental breakdown of this powder. Notice that incredibly high oxygen content sitting at 45%, and the fact that it's remarkably rich in nitrogen at 7.9%. That specific nitrogen richness, that is a total superpower. When you heat chitosan up, those primary amine groups allow it to form nitrogen-doped biochar, which is a really valuable, highly stable carbonaceous material.
Section 3. The pyrolysis puzzle, the chaos of thermal breakdown.
Okay, here is where we hit the central conflict of the study. Turning this amazing powder into clean energy and biochar is incredibly difficult. Why? Because the thermal process required is just downright chaotic. The process is called pyrolysis. That's the thermal decomposition of materials at really high temperatures in an inert atmosphere, which effectively transforms them into biochar and gases. Think of it like baking a highly complex cake. But the chemical recipe of that cake constantly changes depending on the exact temperature of the oven at any given millisecond. That is exactly why pyrolysis is so exceptionally hard to control and predict.
Let's walk through how this builds across the three distinct, totally nonlinear stages of chitosan's degradation. First up, dehydration, where moisture just evaporates between 25 and 75 degrees Celsius. Second is backbone degradation. This happens roughly between 165 and 385 degrees, where the actual glycosidic linkages of the polymer start breaking apart. Finally, char formation kicks in above 350 degrees. The research found that when you hit 600 degrees Celsius, the material undergoes this massive structural reorganization, losing its lamella architecture and ultimately transforming into a highly porous biochar network. But predicting exactly how and when all this happens, it's a mathematical nightmare. The maximum activation energy, basically the energy required to force these chemical bonds to break, spikes to 120.9 kilojoules per mole right when the conversion hits 40%. Because of this drastic mid-process energy spike, standard mathematical models completely fail to predict the chemical breakdown.
Section 4. AI to the rescue. The battle of the algorithms.
So, to predict the unpredictable, the researchers brought in some heavy computational firepower, artificial intelligence and deep neural networks, optimized by meta-heuristic algorithms. To tune the network, they basically pitted two AI optimization models against each other. First, we have Harris-Hawkes optimization, or HHO. This algorithm literally mimics nature, specifically the cooperative surprise-pound swarm hunting behavior of hawks. Pretty cool, right? The second is Bayesian optimization, or BO. This one uses a probabilistic Gaussian process to smartly balance exploration and exploitation of the data. Essentially, these algorithms are trying to automatically find the absolute perfect settings for the neural network without getting stuck in a computational dead end.
But wait, how do we actually know the AI is learning real chemistry and not just memorizing the dataset? Well, the crucial point here is the testing method. Traditional holdout testing is kind of like taking a test where you've already seen some of the answers. There's a high risk of data leakage because data points from the same experiment can end up in both the training and testing sets. So instead, the researchers used group K-fold testing. This is like a completely blind exam. It enforces strict separation, ensuring the AI is forced to predict entirely unseen experimental conditions.
And here is the outcome of that battle of the algorithms. When subjected to that super strict Group K-fold testing, just look at the staggering difference. The Harris-Hawk's optimized neural network took 63 hours to optimize and achieved a 0.960 accuracy in predicting the complex pyrolysis rate. But the Bayesian optimization model, it found an even better neural network architecture in just 4 hours, achieving a higher accuracy of 0.978. BO is drastically faster and way more accurate.
This is a massive victory for the AI. The group K-fold's BO-DNN model successfully predicts the exact rate of pyrolysis, which is known as the complex derivative thermal gravimetry, with an incredible 97.8% accuracy. We now have a robust, highly reliable, and low-cost computational framework for predicting exactly how chitosan behaves under intense heat.
And this brilliantly illustrates exactly what the AI actually learned. Using a game theory technique called SHAP analysis, they asked the AI what variables were driving the reaction. The AI identified temperature as the undisputed driving force, contributing 65% to the variance, followed by time at 20% and the heating rate at 15%. Just like that, the AI successfully unraveled the chaotic thermal puzzle.
Section 5. A sustainable future, from molecules to global impact.
All right, let's zoom back out from the micro-level algorithms and complex chemistry to see how this impacts the real world. The key takeaways here are profound. To prove this wasn't just a one-off fluke, the researchers validated their AI model on entirely different bioplastics, like PLA, and it still predicted their breakdown with near-perfect accuracy. So this isn't just an academic theory. It's a highly efficient, scalable, low-cost framework. It can be used by industries right now to optimize biochar and biofuel yields from all sorts of biological wastes, directly advancing the circular bioeconomy we so desperately need.
It truly leaves you with a sense of wonder about the future of sustainability. I mean, if artificial intelligence can crack the chaotic thermal code of discarded crustacean shells to help fight climate change, what other global environmental puzzles will it solve next? Thank you so much for learning with us on this explainer today. And as always, stay curious.